got the recording going. Let's do this. Hopefully this will work. Come on. Oh, shit. My pencil won't work. But last time I figured out how to make it work. Okay, folks. I solved the problems the other day and made that lecture, but now today, as I'm trying to do it, the problems have come back, and the technique that I developed over a period of hours last time now is not working. It worked the other day, but now it doesn't work, and that's just the way computers are. So I'm not even gonna waste any time, trying to make this work in front of you. It's just not gonna work. So let's just.
Sorry, Professor. You just use rubber instead of pencil.
Oh, really? Okay, let me try that again. Oh yeah, you're right. Okay, let me try it again. Let's try it one more time. We're recording. Share screen. You're right. Thank you. All right. Okay, let's give it a shot now. And so today, the topic of our lecture will be the main topic today is going to be crystal structure. And let's just remind ourselves what we talked about last time. Last time in the lecture that I recorded, and hopefully you guys saw. Oh, by the way, sorry, is everything good? Can you guys hear me? Is it working?
Yeah.
Okay. So last time I discussed bonding. And I just want to say, if you have a question, interrupt me, just ask. It's okay. I like to be interrupted. It's fine. If I'm not looking at the chat as I go along, as I mentioned last time, but if you're in a room with other people, just say, question, look at chat, because you gotta interrupt me and let me know to look at the chat, if that's what you want me to do. Okay, so last time I was talking about bonding, and the reason we were talking about bonding is because bonding is what causes crystals to form. And the idea is that I can take a bunch of atoms that are just in some random, bunch of random atoms that I have. And because of the bonding interactions between them, they will form a crystal, a nice, beautiful crystal like this. And so a good place to start with solid state physics was to discuss the process of bonding. But I will just say the reason that they form a crystal is because the bonding causes the crystal to be the lower energy state because of bonding. And so it is useful in solid state physics to have at least some slight understanding of bonding, even though that's sort of a topic more in chemistry. It's still useful to kind of understand it even in solid state physics. And so I was talking about all the different bonding types last time. The first one I was talking about was covalent bonding, the different types of bonding. And I'm not going to redo all that, but I just will sort of remind you, for covalent, we had, if this is a state of, say, some atom A, and this is axis is energy, and this is another state for some other atom B, then if those two states are, if the atoms are close together such that they hybridize, and hybridize just means that the wave functions overlap. Hybridization is same as overlap of the wave functions. So if the wave functions overlap, as you see in this little picture, then that leads to splitting, and you get splitting. And so you get a state at higher energy, and there's some splitting energy delta, and you get a state at lower energy. And this one we call the antibonding in chemistry, and this one we call the bonding. And so that and this splitting is, you can think of it sort of simplistically as just due to the overlap. So it's really determined by this term HAB that I defined last time, where if I have a Hamiltonian for the system, then HAB is equal to this integral. It's this matrix element of the Hamiltonian between A and B, where I have psi A star Hamiltonian psi B. And I'm going really fast right now because I did this last time, so I don't want to, but I just want to kind of remind you the main ideas. And then we talked about van der Waals, and I'm not going to spell it out, van der Waals bonding. And for van der Waals bonding, the idea is that you can have an atom, or it doesn't even have to be an atom, but something, just some material where I have electrons and protons. And so if this is an atom, then I have a dipole moment that points here. That's the dipole moment. If this is atom number 1, that's the dipole moment. And then if I have another atom here, then the idea of van der Waals bonding is that the dipole moment of one atom will induce dipole moment in the other atom, and then they will attract. So it's kind of a simple idea. And so this dipole, so the polarization, so this dipole moment will polarize the dipole moment in the other atom. That will look like this. Let's say now now the electron goes up here, and then I have a new dipole here, P2. And so now I have these two dipoles, P1 and P2, and you know that dipoles attract. So they attract because they got plus and minus charge, and so they attract. But the attraction, but then we see that this van der Waals attraction is going to go as 1 over r to the 6th. And I did a little. You can derive that using quantum mechanics, but I derived it using just a simple argument last time. And so we see that for van der Waals, if I have two atoms, then I can see that the energy between them you can write as minus A. If it's between atom I and atom J, I have the distance between atoms I and J to the 6th power. But then also there's a repulsive term, which is to the 12th power. And this comes about because of, this comes about because of Pauli repulsion. Pauli repulsion, and I gave an argument for the Pauli repulsion last time, but I will mention to you again, I've never actually seen it derived. I've never seen a formula. I've never seen someone derive Pauli repulsion using quantum mechanics and then say, and therefore it's 1 over r to the 12th. I've never seen that. I've looked in books, I've Googled it, I've never found it. So if any of you can find a derivation of that, I'd love to see it, because it's actually quite important in the real world, but no one seems to know how to derive it. So then if you actually plot this energy between atoms, say van der Waals energy, if I plot Uij, if I have two atoms, then you get this very famous kind of potential where this is the distance between the atoms. And you see this is the repulsive region where they get really close, they repel, And then this is attraction. This is the attractive region. But then you see you got this little minimum attractive region. And, you can measure this thing directly. I mean, we've done it in my lab. I mean, you take an atomic force microscope and you just bring it close to the surface and you can just measure that, that energy, because I can turn it into a force, because force is equal to the gradient of the energy. And so I can just measure the force of an AFM going close, and you can just, and people have done that. It's very common. So you can just directly measure that. And then there's this ionic bonding, which we talked about, and that happens when you have charge transfer. Let's say I have sodium has a very low ionization potential, and chlorine has a really big electron affinity. And I sort of defined all that last time. And then the electron can jump across. This can be plus, this can be minus. Whoops. That's minus. And then you can get the interaction between ions in a salt material, and then you can get the interaction between ions to look like this, plus or minus E squared over 4 pi epsilon naught Rij. That's just the Coulomb attraction or repulsion, depending on, whether the ions are positive or negative or whatever, depending on their signs, the relative signs. But then you also have to look at you also have that polyrepulsion as well. So that's sort of the energy in an ionic crystal. So, and it looks the same. If you plot it, Rij, if you plot it, you're going to get that same very famous kind of look to the energy as a function of distance between the atoms. Although it's going to be, the details will be different from the van der Waals, but it'll have that same type of shape. This is sort of a famous shape that you guys have probably all seen somewhere, or maybe not. But that's the energy of attraction between atoms, energy of attraction between atoms. So it's a very famous plot. And then, okay, so that's what we did last time. And now the new topic is to talk about, well, there was one bonding that I did not discuss. The last one that I wanted to mention is metallic bonding. And so I didn't have time last time, so let's just do it right now. Let's talk about metallic bonding. And so metallic bonding is what happens in metals. And so the idea is that, let's say that I have copper, silver, gold. These are sort of the most famous metals. And the idea is that they have big fluffy orbitals, because this is a 4s orbital. This has a 5s orbital for the valence electrons. This has a 6s. And so if you look at these orbitals, for example, if you look at, let's say, the 4s orbital for copper, and you just plot the wave function of the 4s orbital as a function of distance from the center of a copper atom. If you guys ever done that, then this is what it looks like. It has a funky look to it. It goes woo, woo, like that. And it sticks out pretty far. I mean, like out here is, I don't know, this is like, where the third nearest neighbors are. Third nearest neighbors. I'm not sure I'm getting the distances exactly right, but I think this is around 30 angstroms. I was just Googling it before. I think it's around 30 angstroms. So the idea is that if, let's say I have copper atoms and I bring them really close to each other, then these are like the centers of the atoms. But the deal is that the wave function of the valence electrons is really big. And so it does this, you see, like for each of these atoms. And so you get this really crazy overlap. So you get lots of overlap between the wave functions. And so what you really can do then is just think of a line of metal atoms. It's just sort of like one big orbital. And so then if I have a line of metal atoms, let's say 5 atoms, then of copper, then you would think of it as a box. And so you think of all the electrons as just living in that box. And if this length of this line of atoms is L, then we think of it as a box of length L. And so then you know in a box, you guys, you know that you have a ground state, and then the next energy, you're going to have the next excited state, and then next energy. You guys all know this from quantum mechanics. Those are the eigenstates of a box where this is energy. And so you guys know that for a box, the energy of the nth state is equal to n squared pi squared h bar squared. It's just the famous particle in a box formula that you all learned in quantum mechanics. You might not remember this formula, but go look it up. It's you all have derived it before. And the idea is that you'll notice that the energy, you'll notice that as I make the box longer, bigger, the energy does what? Now I'm asking you a question. I want one of you guys to answer.
It's closer together.
Yes, but all those energies, where are they going up or are they going down?
They're lowering.
Yes, that's the whole point. So for example, look, if I have 5 atoms and then I have a 6th atom right here, that's number 6. The question is it lower energy to have that atom far away or close together? Like, which is the lower energy situation, to have that 6th atom far away or to have it stuck at the end? Well, the answer is that it's lower energy to have that atom stuck, because that makes the box bigger. And so all the electrons go down in energy, because all the states in the box go down. And so that means that last atom wants to stick, because then that will increase the size of the box. Do you see? The idea is to look at the energy before versus the energy after. And if the energy after is lower, then it wants to stick. So hopefully that made some sense. And so that's called metallic bonding. Metallic bonding is just that the box wants to be bigger. Bigger. And the reason is because that lowers the energy of all the electrons in the box. And surprisingly, this same principle explains the UV spectroscopy of large aromatic molecules. So this principle is actually used in chemistry as well, because if I have bigger molecules, then you tend to get all this, they call it red shifting, the energies come down. So
sorry, Professor,
yeah.
Could you explain the logic of this metallic bonding again? I do not very get it. Why the box becomes bigger and there is this bond?
Because you look at this, like this is 2 situations right here that I drew.
Yeah.
I'll call that initial.
Mm-hmm.
And then I'll call this one final. So consider these 2 situations. And so this is what you do in your mind. You say, what is the difference between energy final minus energy initial? And if that is less than 0, that means the energy has lowered. And so in fact, it is less than 0, because in the final state, the box is bigger. And so all the energy levels have gone down. Because in the little box, the energy levels look like this, but in the big box, I'm exaggerating it, the energy levels look like this.
Yeah, I understand this, but why the final state has a smaller box, has a longer box? Because it's
because you added an atom to the end, and so now it's longer, because the length is proportional to the number of atoms. Does that make sense?
Oh, all right. So in the first plot, we are considering the left 5 atoms and the right 1 atoms separately, right?
Yeah.
Oh, all right. I think I understand. Thank you.
Okay. All right. So now, if you then sort of generalize this, to 3 dimensions, life is always a little more complicated in 3 dimensions. And so let's just consider copper again. So, for copper, so let's sort of continue this metallic bonding example. And so let's consider copper atoms. Now, if I have a copper atom, then the valence configuration is going to be 1s2, 2s2. Let's just sort of, I won't always do this, but, just for right now, since this is all sort of new topics, let's write it all out. 3s2, 3p6, 3d10, 4s1. Okay, and so this is the valence configuration of argon. In case you don't remember, that's argon, right? But for copper, we have more electrons, and so this is. But this is a total. But this is a filled shell. That's all filled shell. But this then, right? That's the valence electron of copper, and so that's the one. That's the electron that matters, because the other ones are stuck. But that's the one that can move around. And so if I take a bunch of copper atoms and they're all spherical with that 4s orbital, and I put them together, then the atoms stick together due to the metallic bonding like marbles. Atoms stick like marbles. They're like little marbles. And so what you can do is you can think of the atoms, they want to just stick as close as they can. And if you've ever played with marbles, then like if I take little marbles and I stick them together, they have this this way that they pack this. I'm not drawing it very well, but we call it this close packed. Close packed, close, because they're all close to each other, close packed. So if you take little marbles and you put them together in the most close packed way, then that's how the copper atoms stick together. They just want to get as close as, they just want to suck in and get as close as they can. And the closest that you can get marble spheres is the close packed structure. And so you can think about that. You can sort of prove that. And this close packed structure, it has a name. It leads to a lattice that we'll discuss more, not right now, but in a few minutes. We call it the FCC lattice, and we'll discuss that in a few moments. I just want to give a name to it, though, and also, the copper atoms stick like marbles, but also if you have argon, which has this closed shell that I just drew above. Now, argon has no valence electrons. I mean, there's no extra electrons. All the electrons are in the filled shell. So there's no hybridization. So if I take 2 argon atoms and I put them together, then there's no hybridization. There's no quantum mechanical hybridization that's really occurring because they're closed shell. So they don't do the covalent bonding trick. But instead, they do the van der Waals bonding trick, and the van der Waals bonding of argon does the same thing. You also get they also behave like marbles, and you get the close packed. Oops. You get the close packed FCC structure. And so the reason I'm mentioning this is just because I just want you to know that, quite often atoms behave like marbles. You just squish them together and they're just like marbles. And so you get, looking at the crystal structure of argon and copper, it's just like taking a bunch of marbles and squishing them all together in the most tightest structure, which is the close packed structure. And it's really funny because they're completely different. Copper, it's all hybridized in quantum mechanics and particle in a box and extended states and electronic, whereas argon, there's no hybridization. There's like no quantum, not much quantum mechanics going on, but instead you get this van der Waals bonding, this induced polarization, which leads to the same structure. So that's a pretty common structure. But then things can be very different. But then you can have very different structures. Like, for example, let's consider carbon. And I talked about carbon a little bit last time, but things are very different for carbon. And because for carbon, remember, for carbon, we had the valence structure of carbon is 1s2, which is the closed shell, but then you have the 2s2, 2p2. And then for carbon, those 4 electrons, so these are your 4 valence electrons. And for carbon, you get this thing where you get this tetrahedral structure, and I mentioned it last time, and I'll mention it again today. If you've never seen it, it's a little bit weird. I mean, if you know it, you know it, but if you don't know it, it's a little bit weird the first time you see it. So let's draw a tetrahedron. This is how you do it. I just was reminding myself how to draw these. You draw a triangle, and then you do a little dot there. Then if I can connect these, I can draw a really nice tetrahedron. It's just a 4-sided pyramid. So if you put the pyramid on the base and there's 3 sides to it, and then if I put a little dot in the center, I have these lobes that go to the 4 vertices of the tetrahedron. Okay, that's the tetrahedron. It's 3-dimensional, so I'm not drawing it that good, but you guys use your imagination. It's a 3-dimensional structure like a pyramid. And the 4 lobes, pick a center point, and the lobes are going out to the 4 corners of the tetrahedron. And those are the sp3 orbitals that I mentioned to you last time. And so if I want to create the structure of carbon, then what I have to do is they're all bonding together. And so all these bonds are bonding together, reflecting this weird tetrahedral symmetry shape. And so if I connect all the tetrahedra together, then what you get is a crystal. Then your crystal is what we call the diamond structure. And so it's a more complex structure. It's not just the marbles sticking together. It's a little bit more complicated. And we'll talk about it actually in a few minutes. We'll talk about it more, but it's basically 2 interpenetrating FCC crystals, 2 interpenetrating FCC crystals. So it's more complicated. So I just want to say, I'm just sort of giving you an overview now, just so you get a sense of like how the bonding affects the crystal structure. They're sort of intimately connected. And those are just a couple of examples. And this is also true. This type of behavior I just described is true for carbon, silicon, and germanium. They all have the same behavior in that respect. Okay, so that's just sort of an overview of just some famous crystals. But now let's get more deep into this concept of what is a crystal. Okay, so now we're going to look at things a little from a more fundamental level. So this is sort of a more mathematical discussion now. So let's ask ourselves, what is a crystal in general? And I think you guys all sort of know, or maybe you don't, I don't know, but whatever, it's just a periodic array. It's a periodic array of things. Because you could have a crystal of anything. I mean, you could have a crystal of cars, a crystal of hamsters, squirrels, trees, whatever. You could have a crystal of anything. But in this class, we'll be talking about crystals of atoms. And so it's a periodic array of things. And so you might think to yourself that the concept of the crystal is sort of the central idea of solid state physics, but it's not. There's a subtlety. There's a funny little nuance about solid state physics, which is actually pretty important. And you might not recognize how important it is when you first see it, but I'm telling you now, it's actually very important, because the most fundamental thing in solid state physics is not crystals. There's another concept that's even more important than the concept of crystal. And when you first see it, it's sort of not obvious, but I will tell you, it's the concept of lattice. The lattice is the most fundamental concept in solid state physics. And so this concept of the lattice. So the thing is that sometimes a crystal is a lattice, but sometimes a crystal is not a lattice. And so this concept of a lattice is the most important concept. And we'll do some examples. But let's talk about what is a lattice. So so here's the thing. A lattice has two properties that define the lattice. So the first property is that it's an infinite set of points. And it's an infinite set of points arranged in such a way so that if you stand on any one point, everything looks the same. Infinite set of points such that it looks the same no matter, well, it looks the same. Maybe I'll do it like this. It looks the same from every point. So if you stand on any one point and look out, it looks the same. All right, that's pretty straightforward. And then another way of doing this mathematically is to say it's a set of points defined by this lattice vector by, I can call these lattice vectors. And I can define the lattice vectors like this. And this is in 3 dimensions. N1, A1 plus N2, A2 plus N3, A3 for 3D. And there's only 2 components for 2D and 1 for 1D, such that N1, N2, N3 are integers. And A1, A2, A3 are the primitive, we call them the primitive vectors. Okay, so this is the definition of lattice. And so when you look at that definition, you might think to yourself, hey, isn't a crystal a lattice? Isn't every crystal a lattice? And actually it's not, that's actually not true. Like let's consider some examples. So I'm going to draw some crystals and then you tell me if my crystals are lattices, okay? So here's a crystal. Okay, so here's one. And suppose it just keep going on and on. Okay, so that's a crystal. It's a periodic array of points. You can just see it by looking at it. And so I'm going to ask you, is that a lattice? Does it satisfy these two things?
Yes.
Good. Yeah, exactly. Because no matter where you stand, it looks the same, right? You can just picture yourself, you know, if you're a little man standing here, or if you're a little man standing here, and you look out, you just see the same thing. Okay, now let's draw. So here is a crystal so that's a crystal, and that crystal is a lattice. Now I'm going to draw another crystal. Boink, 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 boink. Okay, and just picture that just continuing forever. Now that's a crystal. I just drew a crystal because it's a periodic array of points, right? It's periodic. It's a crystal, but is this crystal a lattice? Yes or no?
No.
And can you explain why?
I think you would need to have like fractional coordinates, like the ends wouldn't necessarily be integers because there's these spaces in between.
Okay, yeah, I guess that's sort of maybe yes, okay, I guess I have to think about what you said for a little bit, but there's another way of explaining it as well, in addition to what you said, which is that, you know, I just want you to see, like, if you're a little man and you stand on this guy and you look out, you say, hey, there's another atom on my right. But on my left, there's no atom. But now suppose I'm a little man and I'm standing on this guy. I look here, and from that point, there's an atom on my left, but no atom on my right. So you see what I'm saying? If the little man stands on one, everything looks different than if the little man stands on the other one. Do you see my point? I just want you to see, you know, this violates definition number one, the first definition. So that's a really simple way just to tell if a crystal is a lattice or not. You know, like if you have a crystal, if you can stand at one point and look out and things look different than if you stand at another point, then it's not a lattice. It's a crystal that's not a lattice.
What if the little man stands in the middle of the 2 points?
Well, you see, I would ignore that, because when you look at the definition number one says an infinite set of points such that it looks the same from every point. When I say from every point, maybe I should have made let's make this a little bit more specific, from every lattice point. Okay. So so standing in the middle sort of is not relevant to the definition. Does that make sense?
Yeah, that makes sense.
Okay, so I just want to make it as simple as possible. Okay, so now this distinction might seem sort of, you know, like who cares, but it's really important, okay, because it has like vast mathematical consequences, because it's really because where this is leading us to eventually, we're going to be talking about diffraction, waves bouncing around, you know, light waves, vibrational waves, quantum waves, probability waves, spin waves, all this wave stuff where waves are bouncing around. The diffraction of waves is like central to solid state physics, and the diffraction is really determined by the lattice. The primary diffraction properties come from the lattice, not the other stuff. It's the lattice that matters. And so then we ask ourselves, okay, well, if that crystal is not a lattice, then how do I think of it mathematically? And this is how you think about it mathematically. This is how we think of a crystal. So this is what a crystal is. A crystal is equal to a lattice where a basis of atoms is placed at each lattice point. And the basis is equal to an arbitrary grouping of atoms, arbitrary cluster. I'll just call it a cluster. The basis is an arbitrary cluster of atoms. And so now let's go back to my two little examples here. And so you can see here, for the one on the left, this is my basis. Basis equals one atom. And that's when the crystal is equal to a lattice, is when the basis equals one atom. That means I'm just putting one atom on every lattice point. And that's then the crystal equals the lattice. But now let's look at my other one. Here, I'm putting multiple 2 atoms. See, that's my basis. So here, for this other example that I drew, my basis equals 2 atoms. And so that's why this one is not a lattice, because by definition, a lattice, you just have, a lattice has just one point. at each lattice point. And so let's continue with this concept. So what we can do is we now can define this concept of primitive. Let's define this concept of primitive cell. Primitive cell. So these are all definitions that are important, for you to sort of wrap your mind around and feel comfortable with. So let's talk about primitive cell. So primitive cell is the smallest periodic space-filling volume of the lattice. Okay, and let's define primitive, and I'll give some examples. Primitive lattice vectors. Primitive lattice vectors, these define a primitive cell. And so, but here's a trick. This is a nuance to remember, is that they are not unique. Primitive cells and lattice vectors are not unique, and that's annoying. It's slightly annoying, but it's no big deal. It's just part of life. They're not unique. So we pick them by convention. So we pick them by convention. And so you can pick different ones depending on, whatever is convenient for you. We pick them by convention and convenience. Sometimes it's convenient to pick one set versus another. So that's just something you got to get used to. And now let's do some examples, just so you know what I'm talking about. So here's sort of the simplest lattice to think about, is this square lattice. And so you can see what I'm talking about. I'll just, in a minute, it's just so simple if you just look at the example. But okay, so if I looked at this square lattice that I'm drawing here, this two-dimensional lattice, then I could pick this as my primitive cell, right? That's a nice primitive cell. Because it's not in 3 dimensions, it's 2 dimensions, but now in 2 dimensions, you just replace volume with the word area. So you see, this is a space filling, that's the smallest space filling area. And if I just go ka-chunk, ka-chunk, you see how that, if I just pick that square and just move it around, I can cover up all the space. There's no spaces that are left uncovered. It's the smallest space filling area. And then we can say, well, what are the lattice vectors? Well, here's a lattice vector. See, here's one. I'll call that A1. And here's the other. So when I say that these define the primitive cell, that's what I mean. So they're like on the edges of it. You see, those two vectors define the primitive cell. And so those are my primitive vectors. Primitive lattice vectors. And now I say that they're not unique, and this is what I mean. Let's draw, because what I can do is I could have picked this. Check it out. Now I'm going to really blow your mind. Oh my God. Oh my God. Look at that. I could have picked this, see? I could have picked that. I could have picked that, and it's going to have like the same area, but it's just kind of squished over. And so this is another choice. And so then, and I could have picked this. I could have picked this then as my A1, and I could have picked this as my A2. So this
May I
is,
ask a question?
yeah, of course.
So in this second case that you drew, in the first case, you were saying you could kind of pick up that square and move it around and it would cover the whole area.
Yeah.
But in the second case, if you moved it over one to the right, it would go over that little box that you drew. So wouldn't that sort of depend on the edges?
No, it'll work. It should work, because check it out. If I have to continue my crystal out, see? And so see, this is the next one. I moved it to the right. See? It works.
Are we assuming that the crystal is infinite, like it doesn't stop?
Yes, because let's look at the definition of a lattice. Lattice, here, number one, an infinite set of points. See there?
Okay, cool.
Yeah.
Cool, thank you.
Now, of course, in the real life, lattices don't exist. They're not physical, because there's always edges. And so the way we think of it, you know how physicists are, we like to idealize things. And so if someone gives you like a chunk of copper crystal and puts it in your hand and says, how do you describe this? The way that we describe it as solid state physicists, we'd say, okay, well, the way I'm going to describe that chunk of that crystal of copper you just put in my hand is I'm going to think of that as an infinite lattice, because all the quantum mechanical properties and vibrational properties are easy to calculate if it's an infinite periodic lattice. And we were going to do that in this class. That's the purpose of this class. But of course, it's finite. And so what I would do is I would say, oh yeah, it's an infinite lattice, but there are edge effects. I have edges. And then the edge effects you add. You say, so the way to think about it is like, let's think of everything as an idealized crystal, infinite, and try to figure out what those properties are. And then we'll add the effects of the edges afterwards. You see what I'm saying? So that's how we approach this topic. Because edge effects are complicated, that leads to like surface science, it's like a whole science, the science of surfaces, I'm actually a surface scientist. All right. Okay, and so here's a critical thing to remember is that a lattice has just one point per unit cell. And that's an important point, because you can kind of start getting a little confused by these definitions. So they're trivial definitions, but they're actually not that trivial, because you got to remember them all at the same time, and even remembering like 2 or 3 simple things at the same time can become very hard. Sometimes it's not so obvious if something is a primitive, a unit cell or not. It's, I'm giving you these simple examples, but sometimes it's not so obvious. But let's consider this case, and here's a counting trick. Let's check if a primitive cell, how do you check if a cell is a primitive cell? How do we check to see if something is a primitive cell? Well, it has to fulfill these definitions, but sometimes it's sort of hard to test. And so there's one trick, which is the counting trick that I just will show you. I have found this to be quite useful in my life, so I'll tell it to you. It's the counting trick. So let's do this. So let's look at this most simple lattice. And now I'm gonna define a unit cell. And I'm going to ask you, is it a primitive cell? Now, in this case, it's like so obvious, because I picked a really easy one. But suppose it wasn't so obvious, suppose it was a much more complex geometry. So here's what the counting trick is. The counting trick is that there's 1 point per unit cell. Now, how the heck do I get 1 point? So because if I look at that unit cell that I just drew and I count the number of points that I associate with that unit cell, what is the number? Somebody tell me what, just go count them. How many points do you associate with that unit cell? Say
Just
it.
one?
Well, I think it's one, but how can there be one? I mean, if I look at it, don't you see 4? I'm just saying, I look at it, there's 4, right? How do you get 1 out of 4? Can you-
Because only a fourth of each point is actually in the cell.
That's exactly right. Perfect. That's exactly right. Because you say, if I look at each of these points, that point there, I notice that it is shared by 4 unit cells. So in this case, each point is shared by 4. And so then it's each one is only 1/4 of a point. And so then I would say that for this case I have 4 times 1/4 equals 1. So then you go, good, it's a unit cell. And this trick that I'm just showing you is actually useful. Right now, that unit cell is so trivial, you don't need that trick, but there are cases where the geometry gets more complex, and then you actually do resort to these kinds of tricks just to make sure, is what you have actually a unit cell or not. Because sometimes it can be a little confusing in 3 dimensions. Okay, and let's look at it. Here's another important unit cell definition. Let's spell it out. Important unit cell definition. And that is the definition of the Wigner sites. Wigner, I don't know how to say it right. Wigner sites or sites. Unit cell, Wigner sites. It's actually very important. It's used a lot in solid state physics. And so, and the Wigner sites unit cell there's an algorithm to create a Wigner sites unit cell. And the algorithm is connect you want to connect lines to nearest neighbors and bisect them. And to see that, let's draw one. So I'm going to draw a triangular lattice. Triangular lattices are also very easy to draw because then you just draw each line in between the line above it. So this is a triangular lattice. See? A triangular mesh. It's also hexagonal. Okay, so this is a triangular lattice. And so now let's draw the Wigner sites unit cell for this thing. So let's pick, so you just pick a point, pick any point, and then you connect the line. So let's just pick this point right here, and let's connect lines to all the nearest neighbors. And now let's bisect those lines. And I guess it's getting kind of messy, but let's just do it anyways. I bisected that one. I bisected that one. Bisected that one. God, I hope this works out okay. Okay, that wasn't so great, but did I screw that up? I think that's okay. Yeah. 1, 2, 3, 4. Yeah. And so you see that this then is the unit cell. I guess I don't want to fill it. So this then becomes the Wigner sites unit cell is this area inside. Okay. And you can see that it's a hexagon. In this case, in this particular case, it's a hexagon. It doesn't, I mean, for the square lattice, it'd be a square. But the point is that the reason why we like the Wigner sites unit cell is that it's a simple algorithm to construct a unit cell. And the unit cell immediately immediately has the symmetry of the lattice, has the symmetry of the lattice. And you might think, well, doesn't it always have the symmetry of the lattice? But no, I mean, like, look at this case right here that I showed, like, this case. You can see how this unit cell, I'm drawing an arrow to it. See that unit cell? That unit cell does not have the symmetry of the lattice. So you could pick a unit cell that sort of doesn't have the symmetry of the lattice, but the Wigner-Seitz unit cell is very nice because it immediately has all the symmetry of the lattice. And we'll talk about symmetry a little bit more in a moment.
Symmetry.
Yeah, we'll talk about symmetry. In fact, I guess a good time to talk about symmetry is right now. Let's talk about symmetry. So,
Lattice.
I'm sorry.
Lattice.
What are you saying? What? Are you asking me a question? Oh, or maybe you need to be muted or what? All right. So symmetry. I think he's probably using a voice activated thing. Okay, so let's talk about symmetry. What is symmetry? So symmetry is when if I have a lattice and I ask you what is the symmetry of that lattice, then the definition of symmetry is it's a mapping that returns a crystal or lattice to itself. All right, it's a mapping that returns the crystal to itself. And so you can have different, and the mapping and some examples of symmetry are translation. You can have different types of translational mappings. You could have inversion. You could invert the crystal. What else? Can somebody tell me another type of symmetry?
Rotation.
Exactly, rotation. And how about another one?
Reflection.
Good, yeah, exactly. So these are all mappings. And so I can always do the mapping to a crystal. I can always rotate it or translate it or invert it. I can do it. But the question is, if I do that, say, to the lattice, then do the points come back to themselves? Do the points all lie back onto the same points? Or not the same points, but does one set of points then map on to that same set of points after I do the mapping? That's the question. If the points all come back and land again on points and the crystal is unchanged, then I say that that is a symmetry of the crystal. And so let's look at, so for example, if I have, let's consider rotation. Then there's language that we use is we use the language twofold symmetry. And that means that I can rotate the lattice by 2 pi divided by 2 equals 180 degrees. So if a crystal has twofold symmetry, that means I can rotate it by 180 degrees and it comes back to itself. And here's an example of that. What if I have this crystal? So you see that crystal where it's longer in one direction than the other. If I rotate it by 180 degrees, you can see that that crystal comes back on itself. But if I rotate it by 90 degrees, it does not. And so then we can also talk about threefold rotation. Threefold symmetry is when I can rotate the crystal by 2 pi over 3 is equal to 120 degrees. And so an example of that would be the triangular lattice. So then I can rotate that one by 120 degrees and it should come back to itself. And then of course, fourfold. Fourfold is if I can rotate by 2 pi over 4, which is equal to 90 degrees. And of course, the famous example there is just the square lattice. right? That has fourfold symmetry. And then you can keep on going, then we talk about sixfold, 2 pi over 2, 2 pi over 6 equals 60 degrees, etc. So you can, okay, so you I think you get the idea. Now, there is a kind of a funny fact, fun fact, is is that if I give you a lattice, if I give you an infinite lattice, and all lattices by definition are infinite. If I give you an infinite lattice, then I will ask you this question: can a lattice have fivefold rotational symmetry? Yes or no?
No,
Well, can you explain why not?
there's no way to make like that like a pentagon fill all space.
Yeah, that's right. Exactly. So you cannot have the fivefold symmetry. And also, how about sevenfold? It turns out it's the same. There's no sevenfold or higher symmetries, rotational symmetry. So that's kind of a funny thing. Sort of not obvious, when you first think about it, but it's true. And so why is symmetry useful? If I consider symmetry, this concept of symmetry is useful. And it's useful in solid state physics. And there are many reasons why solid state physics, but I'll give you one important one, which is that if if you want to know how a crystal behaves, a crystal is filled with electrons. And so it's the electrons living inside the crystal that give it all of its properties, the electrons. And so to understand those properties, you have to solve the Schrodinger equation. You have to understand the quantum mechanical properties of all those electrons. And so you have to write down a Hamiltonian that incorporates all the atoms, all the lattice and your Hamiltonian, that the electrons are living in this Hamiltonian, right? And so and when you solve the quantum mechanics of the crystal, you have to basically solve the Schrodinger equation for that Hamiltonian. But here's the point, which is that the Hamiltonian of a crystal shares the symmetry of the crystal. And so what that means is that the Hamiltonian commutes with the symmetry operator. I'll just call it Q, the symmetry operator. And so if I define a symmetry operator, that symmetry operator commutes with the Hamiltonian. And so what that means is that our states, our electronic states, we can make our electronic states be simultaneous eigenstates, of the Hamiltonian and at the same time the symmetry operator. So we can construct states, our eigenstates are going to be also eigenstates of the symmetry operator. And that's very useful, because that means then if you understand all the behavior of the symmetries via group theory or whatever, then you can learn a lot about the quantum mechanical properties. And I'm not going to go into that. That's a whole topic in itself, but I'm just pointing out that this is sort of where it comes from. So basically what I'm trying to say is that the symmetry of the crystal has significant consequences for the quantum mechanical behavior of the electrons living inside. And it's a big, big deal. Okay. So
I got a question.
Yeah.
Is there any general proof for the fact that there is no 7 or higher order of symmetry?
Yeah, in fact, there certainly is, of course. I've seen the proof, and
But it's not easy, right?
well, maybe that pentagon space filling concept that the other student mentioned, I think that might be the easiest proof. But there are different ways to prove it. I've seen them. I don't remember the proofs offhand, but I know I've seen them, and There are different ways to prove it.
Thank
And
you.
it's, I don't know, it's like something that maybe you would learn in group theory too. I'm not sure. I can't remember like it where you learn those proofs, but I know I have seen it before. Group theory is where people typically study symmetries, you know, and so, you know, taking a class in group theory is quite useful. Although I would warn you though, be careful if you take a class in group theory to learn, you know, how symmetry affects the behavior of crystals. Be careful which group theory you take, because in the world of mathematics, like if you go to a math department and you take a group theory course, which I did stupidly when I was an undergrad, like I took this whole group theory course and they just talked about all this weird, useless, or to me at least, I'm not a theorist, so I found it all quite useless. And never once did they talk about rotational symmetry. And I was like, what the hell? You know, I took a whole group theory course and never once did they even mention rotations. And so that, and the reason is because mathematicians think of group theory differently than physicists. You know, as physicists, when you say group theory to a physicist, the physicist says, oh yeah, you know, that group theory helps me to understand how the different symmetry operators affect the quantum mechanical properties of my system. And it's so important. That's how we think, but mathematicians have a different take on it. So if you take a group theory course, make sure you take the right course and maybe one that's more applied and not like the total abstract one. Because, you know, the abstract math group theory, well, I would just say in my personal opinion, I found it to be like totally useless. I didn't talk about any of this stuff, but I'm not a theorist. If I was a theorist, I'd feel very differently. I'm an experimentalist, you know, and so I'm not like really into like really fancy theory, but other people are. So that's just a personal preference. Okay, so let's keep talking about crystals. And so if we talk about three-dimensional lattices, then it turns out, you know, I defined lattice to you, you know, just those two simple definitions. And so now, so a lattice is just this, you know, infinite set of points, right? That you stand on one, it looks the same. No matter which one you stand on, it looks the same. You know, that's a lattice, such a simple definition. So now I will ask you a question: how many different types of lattices can you have? How many exist? I'm gonna hold on one second. I'm gonna do something. Hold on. And let's define the lattices by saying that the different lattices will have, say, different symmetries, you know, because that's how I will define two lattices are different because they have different symmetries. You know, they might have some different inversion, reflection, whatever. So how many different types of lattices are there? Does anybody know? In 3 dimensions. Now, if you already know the answer because you learned it in another class, that's not fair. But, you know, I'm asking people who, you know, haven't learned this. There's an answer to this question. And if you, and I'm only asking the people who, you know, haven't seen this before, who are taking this for the first time. So okay, I'm asking for an answer. Tell me, just make a guess.
6.
Say it again. Say it again.
6.
Okay, that's a good guess. Anybody else have any? I mean, you know, I would have guessed infinite, you know, I would have said infinite, you know, just there must be an infinite number, but you said 6. So you're actually, that's a better answer than my answer. Okay, so the answer, let's not belabor this too much. The answer is that there are 14. 14 different lattices exist. So, I mean, so, you know, that's good and bad. You know, the good part is it's only 14. Hey, that's not so many, you know, but the bad part is that 14 is kind of a big number, you know, it's like, that's actually a lot of lattices. Like, I mean, who could, and each lattice is like a little world unto itself, you know? And so I will just mention, you know, the different lattices. There's triclinic lattices, and you will see pictures of these in your book. I'm not going to try to draw them, but there are triclinic lattices, monoclinic, and each of these lattices has different symmetry properties, orthorhombic, tetragonal, cubic, trigonal, hexagonal, And for monoclinic, there are 2 types. And for orthorhombic, there are 4 types. Tetragonal, there are 2. God, I hope that these add up to 14. 1, 1, 1. That's 7, 8, 9, 10, 11, 12, 13. Yeah, that has 14. Okay, so those are the 14 different types, pictures of lattices in book. So go look them up and take a look at them. I just want to say that there's a lot of details there. You know, each of these lattices has all these details. You know, each of them is like a little world unto itself. And the point is, nobody like remembers all the details of all these lattices. So solid state physics does not mean that you have to sit there and memorize all these structures and remember all the properties of all these lattices. You know, don't do that. That's a waste of time. But it's just a fact that these lattices exist. And so what happens out in the real world is that people tend to sort of study only like, I mean, most people in solid state physics are studying a material, and each material to study it takes a while. So somebody might be studying silicon. So someone who studies silicon might be studying silicon for like, you know, a few years or a lifetime, or somebody might be studying graphene. Like I study graphene, so I've studied it for years. So solid state physicists tend to glom onto a solid that they like to study, and they will study that for a long time, you know, maybe months, years, whatever. And the point is that that solid is going to have a crystal structure. So if I'm studying silicon, then I'm going to like know the crystal structure of silicon, and I'm going to remember all those details, but I'm not going to remember the crystal structure of magnesium. You know, I don't give a damn about the crystal structure of magnesium. You know, I'm studying silicon. So that's my point, is like, you know, if you're studying a particular material, then you got to learn all the details about the crystal structure of that material. But nobody needs to remember all the crystal structures of every material. So I just want to just tell you, you know, you're not expected to understand all these crystal structures and all their details. But that said, there's still a few details that pop up a lot in solid state physics. So for example, the most common crystal structure, or one of the most common crystal structures, is cubic. That crystal structure pops up a lot. And so there's, so these cubic, see how this thing keeps popping up saying, allow this device? That's the problem. When that happens, what I have to do is I have to reboot my computer and the iPad simultaneously to make that stop happening. I'm not going to do that now because we only have a few minutes left in this class. But the most common, one of the most common lattices are these cubic lattices. And there are, as I said here, there are 3 different types. So let's just spend a moment talking about cubic lattices, because these are very common. And so it's worth just looking at the details a little bit. But I just want to say, like, if you go and are doing research, you know, your crystal, if you're doing like, you know, high TC, you might be doing orthorhombic, you know, crystals or whatever, you know, but let's just talk about cubic. So there's 3 types of cubic lattice. And the first one is the simple cubic. And that one looks like this. It's sort of the one that you would draw, the most simplest one. So if I put atoms at the corners of cubes, and then if I just take these cubes and just go use that as a space filling unit, so I'll go boop, 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 and make the crystal, that's the simple cubic. Simple cubic. But then another very important one is, and there are no, I don't think any elements, there are no elements that form this. So this one is actually not so common, the simple cubic, but there's another one which is called the face-centered cubic. Face-centered cubic. And that one looks like this. You draw your cube, and we have atoms at every corner. But then we also put an atom right in the center of each face. Like this face gets an atom, this face gets an atom, this face gets an atom, that face gets an atom. Every face gets an atom. Okay, you see what I'm doing? I'm putting an atom at the center of each face of that cube. So that's why it's called face-centered cubic. And this one is super common because this is what you get when you have close packed marbles. Close packed marbles do this. They give you the FCC. So it's really the tightest structure. And this is the structure that you get when you have, for example, copper, gold, and silver. And because it's the tightest structure, you have many glide planes. It's easy to deform. So because it's so tight, there are many glide planes. It's very easy to just go and just change it a little bit, and it's like the same, you know. And so that's why copper, gold, and silver are soft. So FCC metals are known to be soft, whereas there's the third type of one is body-centered. Body-centered cubic. And the body-centered cubic is the same. You do the same thing. You draw your cube, and you have atoms at every corner. But now you put an atom right in the center of the body, and you take that and you repeat it, up, and that's the crystal. And this is a different structure than the face-centered cubic. It has a different set of symmetries, and it's more. So the materials that have this tend to be stiffer. So the materials that have this, for example, are vanadium, niobium, tantalum, tungsten, moly, chromium. These are all iron. These are metals that are more stiff and brittle. And that's because there's less glide planes. It's not as tight of a structure, so it's harder to change. And so those materials tend to be more stiff and more brittle than copper, gold, and silver. So those are just some little facts, fun facts that, you know, it's just kind of nice to remember, kind of useful little facts to remember. And then what we can do then, of course, there's another very famous, structure, which is the diamond structure. Diamond, which is made out of carbon, right? It's just all carbon. And the thing about diamond is that the diamond is, or it could be all carbon, or it could be all silicon, or it could be all germanium. And the diamond structure is FCC, face-centered cubic. So this is we call FCC, and this we call BCC, body-centered cubic. The diamond structure is FCC, but with two atoms, but with a two-atom basis. So to get the diamond structure, you basically take the FCC lattice, but at every lattice point, you put two atoms, which are displaced from each other. And it's two carbon atoms. And so that's the diamond crystal. It's the FCC lattice, but with a two-atom basis. And so that's the diamond structure. So the diamond structure is this. And also another very famous structure is the sodium chloride, salt. And the sodium chloride structure is the same thing. It's the FCC, but now with here the two atoms are the same, like silicon, carbon, or germanium, but with sodium chloride, it's an FCC structure with a two-atom basis, and the two atoms are different because one is sodium and one is chlorine. All right, so that's how, and so I would say the diamond is a crystal. Diamond is not a lattice, but the lattice of diamond is FCC with a two-atom basis. All right, so you see the difference? And so that's really important to understand. And then I will just mention another very famous structure The last one I will mention, then we'll stop, is hexagonal close pack. Hexagonal. So these are the most common crystal structures, although, you know, other ones exist, as I mentioned, but these are just really common ones. And so this is simple hexagonal, but with a 2-atom basis. And so I will just tell you what simple hexagonal is. Simple hexagonal is you just draw a hexagon, and then you draw another. It's actually kind of hard to draw. And you put atoms here and here, here, and also at the center. And you go like this. These are just dashed lines. And then you just kind of connect all these things. You connect all the atoms. So I'm not very good at drawing this. But you see, it's sort of you get these prisms. You get like these 6 prisms. And so that's the volume of, that's the simple hexagonal unit cell. And then if you put 2 atoms in the basis, then you get the hexagonal close packed, which we call HCP. And HCP is very common. And so you would put another couple of atoms in there. I just can't draw it. Like you'd put one here. I can't really draw it. It's too hard. But the reason I mention is because there's a lot of materials that have this structure, the hexagonal close pack, such as zinc, cadmium, beryllium, magnesium. Okay, folks, that's it. So we'll stop here. Bye-bye.
Thank you.
Okay.
Bye-bye.
Thanks.
Bye.